Okay, welcome back, guys. So we're going to finish up 9.6, and we're going to look at solving logarithmic equations. So these are just equations that have logarithms in them, okay? So you can see some examples here. Sometimes they may only have 1, 2, 3, okay? Alright, so we'll get started. Now, you have to remember when you have, what is a logarithm? Log base a of x equals y. What does that mean? Well, that means this right here. And if you recall from 9.4 when we studied those logarithms, this is the way we would convert a logarithmic. In trying to evaluate a logarithm, we would look at it from this perspective. Okay. The answer is y, and so we would think about a to what power y is equal to x, okay, or is equal to the argument of the logarithm. Well, what we're going to do to solve these logarithmic equations is we are going to convert them into exponential equations. Okay. Now, sometimes we may have some preliminary work first. So, for example, I can't do this unless I have just one logarithm. Okay. So if I have 2 logarithms or 3 logarithms, and somehow I need to condense that down to just one logarithm. So hence our work in 9.5 in condensing those logarithms. Alright, well, let's take a look at example 7. And by the way, when you convert a logarithmic equation to an exponential equation, that is called exponentiating. Okay. Oops. I don't know if I can spell it right. Exponentiation. Okay. So it just means that when you have this logarithmic relation right here, you're just converting it to an equivalent exponential relation. That's all. Okay, so let's take a look at this first one. This is log, the common log of x is equal to -4. So we're trying to figure out the common log of what number x would be equal to -4. Well, we're going to exponentiate this. And to do it, you've got to remember that the common log has an understood base of 10. Okay? Because when I exponentiate this, this will become 10 to the -4 power is equal to x. Okay, we got some practice doing this in 9.4, converting a logarithmic equation to an exponential equation and vice versa. Okay, so that was the reason we did it, is because this is the way we're going to solve these, or this is part of solving these logarithmic equations. Well, guys, when I simply exponentiate this, it's pretty much solved for x. It just says x is equal to whatever 10 to the -4th is. If you remember your rules of exponents, this is the same as 1 over 10 to the +4. And that would be the same as 1 over 10,000. Okay, 10 to the 4th is 10,000. So this is my answer right here. Now, if you want to convert this to a decimal, that's fine. It would be 0.0001. This is not an irrational number, by the way. This is a rational number because it's a fraction. All right. What about, and if you recall when we were working with those logarithms, so if x is this fraction, 1 over 10,000, I mentioned that whenever you're taking the logarithm of a fraction, the answer is going to be negative, because this base only raised to a negative will give you a fraction. Okay, typically it's going to be a negative number. All right, well, let's look at example 9 then. Example 9 is similar. We just have one logarithm. Okay. Now the base is 5 and the argument is this 8 minus 7x. So when we go to exponentiate it, it will become 5 to the third power is equal to 8 minus 7x. There we go. Alright, well, what is 5 to the third power? Well, that's 5 times 5 times 5, which is 125. Let's recopy everything else. And now, guys, when we exponentiate it, we end up with just a linear equation here. So we can solve this for x. We'll subtract 8 from both sides. Let's see, 125 minus 8 is 117. And this is equal to negative 7x. And we'll divide both sides by negative 7. And we get that x is equal to, this is going to be an irreducible fraction, negative 117 over 7. Okay. Now there's one thing that I want to point out here. If you remember, the domain of a logarithm, or of a basic logarithmic function, was from 0 to infinity, not including the 0 though. In other words, we said that we cannot take a logarithm of a negative number. So when you're solving these logarithmic equations, you really need to check your solution to make sure that the argument of this logarithm doesn't become negative. Now, this does not mean that your solution can't be negative. See, my solution's negative here. This means that when I plug this back in, if this argument of the logarithm becomes negative, then that will not work. Okay. But if I were to try to do this, I just want to ensure that the argument of this logarithm remains positive. Okay. So I will just type in 8 minus 7 times, and then in parentheses plug in my solution that I came up with, negative 117 over 7. As long as this is a positive number, then I'm okay. Okay. So this is the solution here. Alright, so remember, you need to check let me actually write this out just to show you. So, and this equals 125. So, and then you could even evaluate this further. Log base 5 of 125 is 3, because 5 to the third power is 125. Alright. Now let's look at these last 3. Okay, these are going to be a little more involved simply because we have more than one logarithm. So see, I can't just simply exponentiate now. I need to first combine these two logarithms on the left-hand side. And so the way we do that, guys, is using the product rule that we talked about in 9.5. The reason I know we're going to utilize product rule is because these logarithms are separated with addition, or in other words, I have a sum of logarithms here. So I can condense these down into one. This will be the common log of x times x minus 9. Okay, so all of this right here is my argument, and then this is equal to 1. Now what I could do next, before I exponentiate, because see, I do now have just one logarithm. What I will go ahead and do, though, is distribute this x through here. And so if I do that, I have the common logarithm of x squared minus 9x, and that's my argument. And then this is equal to 1 again. Now I'll go ahead and exponentiate this. But again, I've got to remember that because this is the common logarithm, the base is understood to be 10. Okay, so I'm going to come over here to the right to show this. This will become 10 to the first power is equal to that argument, which is x squared minus 9x. And of course, 10 to the first power, that's the same as 10. And when you look at this equation, guys, this is actually a quadratic equation, isn't it? And we got a lot of practice solving these quadratic equations. What I'm going to do is put this in standard form, so I'm going to subtract 10 from both sides, so that'll just move this 10 over, make it a negative. Okay. And then you can solve this quadratic equation either using the quadratic formula, or you can factor it. This one is factorable. Factors of negative 10, I'll show you, that sum to negative 9. Those factors would be negative 10 and 1. Okay? And so this would factor x minus 10 times x plus 1. And remember that relationship between factors and zeros. So if these are my factors, then my zeros, or in other words, the values for x are going to be positive 10 and negative 1. Okay? Alright, so I arrived at two solutions, so now I need to check these. You can typically do this just by inspection, guys. Remember, arriving at a negative solution doesn't mean you have to throw it out. You just have to make sure that the arguments of the logarithms don't become negative. Okay? Well, I'll start with 10. If I plug 10 in for x, then 10 minus 9 is 1, so we're okay there, and then this argument would just be 10. But if we plug in negative 1, then we've got a problem. Because negative 1 minus 9 is negative 10, so then I'll be trying to take the logarithm of a negative number, and we can't do that. And furthermore, if I plug negative 1 in for this x, then I'll be trying to take the logarithm of a negative again. Okay? So it's a bit of a coincidence that we have to throw out that negative number. But we throw it out or discard it because it makes these arguments negative. And so we wouldn't be able to actually evaluate the logarithm. Okay, so the only solution here then is 10. So again, guys, like I said, you need to check your solutions. Okay? Alright, now let's take a look at example 11 here. This one's interesting because what we have here is we got two logarithms on the left-hand side and a logarithm on the right-hand side. Well, the first thing I'm going to do is try to combine these two on the left-hand side. And I notice that they're separated with subtraction. So that's an indication that I will combine them or condense them using the quotient rule. Okay, so this will become log base 2 of the quotient of those two binomials, x plus 20 over x plus 2. Okay, so this is the argument, new argument, and then this is equal to log base 2 of x. Alright, now, in a situation like this, when you have logarithms on both sides of your equation, then you don't have to exponentiate. Because we have log base 2 on both sides, log base 2 of this argument being equal to log base 2 of this argument, this implies that those two arguments must be equal. So this implies that x plus 20 over x plus 2 is equal to x. This is similar to what we did when we were equating the bases. And so now you just need to solve this equation right here. Okay. Well, to solve this one, guys, I've got a denominator here. So I need to multiply both sides by this denominator. So, let's see. Well, in other words, yeah, you're just going to multiply both sides by x plus 2. And then, okay. So, on that left-hand side, and again, this is the reason we do this, those x plus 2's divide out. And so we're just left with x plus 20, and that's equal to whatever this becomes. x times x plus 2. And what I'll do here is distribute this x, and I think we're going to end up with another quadratic equation. Okay, because x times x is x squared, and x times 2 is 2x. We copy my left-hand side. And now you can see this is, in fact, a quadratic equation. Okay, so I'm going to try to get everything on one side. I'll move the x and the 20 over to the right. You can do it in one step by subtracting both of them. So on that left-hand side, we're going to be left with just 0. And again, we're putting this quadratic equation in standard form. We'll have x squared. 2x minus 1x is just x, and then we'll have minus 20. And interestingly, guys, this one is factorable as well. Or you can use the quadratic formula. It doesn't matter. Yeah, so I'm going to factor this. Factors of negative 20 that add up to 1, 5, and negative 4. So my factors would be x plus 5 times x minus 4. Okay, and if this product is equal to 0, then this implies that either both or one of these factors is equal to 0. So, you know, technically we'd set them equal to 0, and we'd solve them both for x. But you know, that relationship, or that relation, is that if you know the factors, you know the zeros. They just have the opposite signs. So these would be the two values that we get for x. Negative 5 from this factor, and then positive 4 from this factor. Alright, well, we need to check these again. Okay. So I'll check the 4 first. I'll plug 4 in. This argument would become 4. This one would become 4 plus 2, which is 6. This one would become 4 plus 20, which is 24. So we're good. No negatives. But if we plug negative 5 in, then this argument becomes negative 5, and this argument becomes negative 3. Okay? So negative 5 is not going to work as a solution. So I'll eliminate negative 5. And so therefore, the solution to this particular logarithmic equation is only the integer 4. Alright, 4 is the only number that will work. And again, you could check this one if you wanted. You could take 4 and plug into these x's, plug all that into your calculator. Alright. Well, let's look at one more here. Example 12. Okay. Again, I'm going to start off, guys. I notice these two logarithms are separated with addition. So I'm going to condense these using the product rule. So this will become log base 4 of the product of those two binomials. X plus 3 times x minus 3, and that would be equal to 2. So it looks like we'll be able to exponentiate this one. Okay. However, before I do that, I'm actually going to go ahead and multiply these two binomials. Now if you notice, these are conjugates, so the outer and inner two terms will cancel. So all we would end up with would be the first and the last. So x squared minus 9. So that is our argument. And now if I proceed to exponentiate here, this will become 4 to the second power is equal to x squared minus 9. And interestingly, again, this is another quadratic equation, isn't it? Well, here, 4 to the second power, that is 16. Okay. And this is one because it's missing the middle x term. We can solve it directly for x, if you recall. I can add 9 to both sides. So I'll get x squared is equal to, that'll be 25. And then I can take the square root of both sides. Remember, we refer to this as the square root method. Remember, you get a positive and a negative root here. So the square root of x squared is x. The square root of 25 is 5. So we obtain both positive and negative 5. All right, well, now we need to check which of those, or maybe they both work, are going to be valid solutions. Well, if I take positive 5 and plug in for these x's, these arguments are going to stay positive. But if I take the negative 5 and plug in, both of the arguments will become negatives. Okay? So the negative 5 is not going to work. And so our only solution is 5. And guys, let me show you real quick. You know, if you were to try this, go to math, go down and get your log base, and type in there log base 4 of, well, you can plug negative 5 in for this x, so it would be negative 5 and then plus 3, close those parentheses, and you could say plus, do the same thing for the second logarithm. Log base 4 of negative 5 minus 3, okay, close those parentheses. Now this should equal 2, but if you hit enter, it says non-real answer. And again, the reason is because these arguments become negatives, and you can't take the logarithm of a negative number. Again, a negative is not in the domain of a logarithmic function. What happened?